If you just have a look at page 7 of your worksheet, we'll be continuing on from photoelectric emission. So page 7 is on November 15 P43. So if you just look at the question now, they mentioned that you have light of wavelength lambda that is incident on a metal surface having a work function energy of 5. Photoelectrons of maximum kinetic energy Emax are emitted from the surface. State an equation relating phi, the work function, Emax, the maximum kinetic energy, and the wavelength lambda. Explain any other symbols that you use. So this one is actually describing photoelectric emission. So when it comes to photoelectric emission, there is an equation that describes that phenomenon. So you have to write it out. In your case, the general form was energy of your photon equals to your work function plus your KE max of your electrons. So you are required to write it in a proper equation using the symbols that have been defined in your question here. So when you're talking about energy of photon, we know it is actually going to be either HF or HC over lambda. So for energy of photon, we will just use HC over lambda here, following what the question gave us. And then when it came to your KE max, or your maximum kinetic energy of electrons, is already defined as E max here. So you just put E max here. And then lastly, your work function, which is the minimum energy of photon required to cause photoelectric emission. This one is already defined in your question too, given with the symbol phi. So you just put the work function as symbol phi here. Okay, so the question asks you to define any other symbols that you use. So for the other symbols that you have used here, you have Planck constant, which was not defined inside the question, and also the speed of light, or rather the speed of EM radiation, which was also not defined. Okay, so you write this equation here, you will be getting your 2 marks. All right. Then you look at part B. For part B, they mentioned to you that the variation with 1 over lambda of Emax is as shown in the figure below. Now, by reference to your answer in A, explain why the gradient of the line does not depend on your metal surface. So if you refer to the equation that you have actually done in A, is HC over lambda equals to Emax plus phi, you try to rearrange the equation such that it is in the form of y equals to mx plus c. You can see here that your y-axis is Emax, your x-axis is 1 over lambda. You try to rearrange it in the form of y equals to mx plus c. You should be getting something like this right now. Emax is hc over lambda minus phi, where your y-axis is your Emax and your x-axis is basically your 1 over lambda. Okay, and then your y-intercept is going to be negative 5, but the one that you want to look at right now is actually your gradient. Your gradient is actually hc itself. Okay, so your gradient is hc, y-intercept is negative 5. So why is it that the gradient does not depend on the metal surface that you use? Because the gradient is actually the product of two constants, your Planck constant and your speed of light. So since both of them are constants, your gradient won't depend on the metal surface that you use. Okay, so that's the actual answer. You just need to say that because the gradient is hc, and because hc are constants, therefore your gradient will always be constant throughout, regardless of whatever metal that you use. Okay, so this is another 2 marks, which is pretty straightforward. Okay, then let me just clear out the diagram and move on to part 2. Now here they mentioned to you that the work function energy of sodium is 2.28 eV. Determine the minimum wavelength lambda naught at which Emax is 0. Now this one, there's something a bit odd about this question. When your Emax is 0, you are supposed to be at threshold wavelength. And when you are at threshold wavelength, that is actually the maximum wavelength to cause photoelectric emission. Maximum wavelength to cause photoelectric emission. So anything more than that, you will not get photoelectric emission. Anything less than that, you will get photoelectric emission. But somehow or another, they use the term minimum wavelength here, which is a bit odd. It should have been maximum wavelength. All right. So, but regardless, you can still do the question. If you want to find out the minimum wavelength or maximum wavelength lambda naught at which your Emax is 0, this is actually talking about your threshold wavelength. So what you could do, if you remember from what we did last lesson, it was mentioned to you that if you look at your photoelectric equation, Hc over lambda equals to Emax plus phi, at lambda naught, your threshold wavelength, your Emax will be 0. So this equation that you have here, this one would be 0, and then this one would be lambda naught. Eventually, your equation simplifies to Hc over lambda naught equals to 5. You can actually just start off with this equation straight away without doing whatever is at the top there. Okay, the top part is actually kind of like explanation. In your exam, you can actually just start from here straight away. Hc over lambda naught equals to 5. And then after that, you just sub in the relevant values to get your threshold wavelength. So your Planck constant being 6.63 times 10 power minus 34, you can get from your data sheet. Your speed of light is 3 times 10 power 8. You can also get it from your data sheet if you haven't remembered it already. So divide it by your threshold wavelength, equate it to your work function of 2.28 eV. So this one, you need to be careful to remember to change your EV values to joules. So if you recall what you learned previously, 1 EV is 1.6 times 10 power minus 19 joules. So you need to multiply with that value to get it in joules. So eventually your threshold wavelength will become 5.45 times 10 power minus 37 meter, just like that. Okay, so this is another 3 marks. Okay, so next question that you can then look at is, I believe, page 8. Okay, you can then look at page 8 for your next question. So if you have a look at page 8, this one is the next part of your question. So with reference to the photoelectric effect, state what is meant by your threshold frequency. So threshold frequency is simply the minimum frequency of electromagnetic radiation which can cause emission of electrons from the surface of a metal. So when it comes to threshold frequency, it is minimum frequency to cause photoelectric emission. But when it comes to threshold wavelength, it is maximum wavelength to cause photoelectric emission. They have an inverse relation because frequency is inversely proportional to wavelength. Okay, if one of them is max, the other must be minimum. All right, so that one okay. Now, if you look at B, in B, you have electromagnetic radiation of wavelength lambda that is incident on a metal surface. Electrons of maximum kinetic energy Emax are emitted. On the figure below, sketch the variation of 1 over lambda. Sketch the variation with 1 over lambda of Emax. So it's the same exercise as before. Your equation is HF equals to Emax plus phi. You change it to Emax equals to HF minus lambda because you're trying to change it in this form, y equals to mx plus c. But because right now you're not dealing with frequency, but instead you're dealing with wavelength, your HF here, you eventually need to change it to hc over lambda. So your equation becomes Emax equals to hc over lambda minus phi, from which you already should know from the previous question, gradient is your hc, your y-intercept is your negative wave function. Okay, so for this part alone, you should already know is a straight line with positive gradient and negative y-intercept, just by looking at the form of the equation here. I mean, if I try to rewrite it properly, this one is actually E max equals to HC 1 over lambda minus 5. You can clearly see that it will be a straight line with positive gradient and negative y-intercept. Okay, because here you can see that this one is positive gradient, this one here is negative y-intercept. Okay, so just draw that line. That line will be this one. Okay, because it doesn't go below the x-axis, you just draw it halfway and terminate it right over here. Okay, there's no need for you to extend it all the way to the bottom because the bottom part isn't reflected inside your question. So then you move on to the next part of your question. State an equation relating the gradient of your graph drawn in the figure to the Planck constant h. Explain any other symbols that you use. So this one, we already know that gradient is actually equals to your hc. So what other symbols have not been explained here? That one is your speed of light. Okay, so that one is for this question. Planck constant is already explained inside your question. They already told you there's an equation relating gradient of the graph with Planck constant h. So there's no need for you to define what is the Planck constant h again, since the question already described it to you. Okay, then you move on to part 3. Let me clear this thing off. Okay, so for part 3, explain why for any particular wavelength of electromagnetic radiation, most of your electrons are emitted with kinetic energies less than the maximum kinetic energy value. Okay, so this is a standard question that tends to come up quite often. That is usually worth 2 marks. So the first statement you always tend to write is this: the electrons at the surface are emitted with maximum kinetic energy. For electrons below the surface, energy is required to bring them to the surface. Therefore, their kinetic energies will be less than maximum value. Okay, the first statement here is worth 1 mark. The second statement here is worth the other mark. Okay, so if you want to visualize it, you can just imagine it as something like this. Let's just say, for example, this is your metal. Okay, and your electrons are spread out throughout your metal. So your electrons at the surface, which is basically this region here, if your electrons here receive your photons, these are your photons, the electrons at the surface will actually require the least energy to escape. It will require the least energy to remove from the surface. So whatever energy or photon you receive, you actually have a larger balance of your photon energy remaining that can be converted to KE. Therefore, your KE here is supposed to be max at the surface. All right. But if you're talking about electrons that are below the surface, like the ones that are right over here, your electrons will still be able to escape. Okay. But before they can escape, you need to use energy to bring them to the surface before they can even escape from the surface. So if they are from here, you need to go up in the first place before you are even able to escape from the surface. And this requires energy. So that energy actually came from your photon energy. So since energy is used to bring them to the surface before finally removing them, you actually will have less balance of your photon energy remaining to convert to KE. So even though your electrons escape, KE is not going to be maximum. It's actually going to be some value that is lesser. Okay, so that is how you generally try to understand this question. Okay, then there's another part to this question in the next page. If you just look at the question now. So for part 4, they mentioned that light of a particular wavelength is incident on a metal surface and gives rise to a photoelectric current. So the wavelength is reduced, but the intensity of light is kept constant. From there, state and explain the effect, if any, on your photoelectric current. Okay, so you will notice that sometimes they use the terms photoelectrons and sometimes they use the term photoelectric current. So in the first place, what are photoelectrons? Photoelectrons, I believe I already mentioned this inside the notes before. Your photoelectrons are actually the electrons that are emitted from photoelectric emission. Okay. And then after that, when you're talking about your photoelectric current, is actually the flow of your electrons that are emitted. In other words, it's the flow of your photoelectrons from photoelectric emission. Okay, so one way to kind of like visualize it is something like this. If you imagine that this is the surface of your metal, and you have these electrons here, when photons come towards the surface, your electrons accept those photons, and if it's enough energy, they will escape. So the electrons that have escaped, which are this one, these are known as your photon electrons. Okay, and then when they flow towards one side in a particular direction, those are known as your photoelectric current. Okay, so that's just one thing to note here. Now, if you look at your question, what they want you to do now is to explain the effect on your photoelectric current when they reduce your wavelength of your photons, but keeping the intensity of the light constant here. Now, if you recall what intensity was, intensity of your light or intensity of your photon is defined as power per unit area or total energy of photons divided by time times wave area. And then this one here, your E total is your total energy of your photons, which can then be further expanded to become N times E. Okay, so this one, let me just rewrite this, which can be further expanded to become N times E divided by T times A. Okay, so the E here that you're looking at is the energy of a photon only, whereas the N that you see here is the number of photons. Okay, so right now there are certain things that you want to look at. They told you in the first place that your intensity of light is kept constant. Okay, your intensity of light is kept constant. And you can also assume that the area at which your photons are incident on are also constant. So from there, you can actually make some sort of conclusion. Let me just rearrange this equation here. You can actually say that from this intensity equation, number of photons per unit time is actually equals to your intensity multiplied with your area divided by your photon energy. And then this is what you can actually see from here. Now, if intensity and area is constant, that would have meant that number of photons per unit time is actually inversely proportional to your photon energy. This is relation number one. Okay. Now, from there, they did mention to you that the wavelength has been reduced. This one will have an effect on your photon energy because photon energy is defined as either HF or Hc over lambda. Now, H and C by themselves are actually constant. Therefore, your photon energy is inversely proportional to your wavelength. If your wavelength is now reduced, it follows that your photon energy must increase. Okay, so this is another relation that you can actually kind of deduce now. Because your wavelength has been reduced, your energy of photon must therefore increase. So now if you look at the first relation that you actually derive from here, because N over T or photons per unit time, this one I think I better write it now. This one is photons per unit time, not electrons, okay? Photons per unit time. This is photons per unit time. So if your photons per unit time is actually inversely proportional to your photon energy, this one let me just write it here. From 1, since number of photons per unit time is inversely proportional to your photon energy, if your photon energy now increases, the number of photons per unit time decreases. So this actually tells you one thing. You have less photons per unit time incident on the metal surface. So since you have less photons per unit time here, that means your electrons are receiving less photons. So when your electrons are receiving less photons, it thus follows that you have less electrons emitted. So here, you can then actually work out some sort of conclusion. So since you have less photons per unit time incident on metal surface, therefore less electrons are emitted per unit time. And right now, when you're talking about electrons emitted per unit time, this is actually referring to your photoelectric current. Because just now I told you that when you're talking about photoelectric current, it actually refers to the flow of your photoelectric electrons or your photoelectrons. Okay, so less electrons emitted per unit time, less photoelectric current. So you want to work out your answer, it will be something like this. When your wavelength is reduced, the energy of photon increases. Since your intensity is constant here, there are fewer photons per unit time. This is actually related to this particular equation here. And then for the first statement, is actually related to this statement here. Okay, so since you have less photons per unit time, this causes fewer electrons emissions per unit time. Therefore, your photoelectric current is going to be less. Okay, so for page 35 is November 2019, P41. We'll go through that now. Okay, so from there, if you look at the question, with reference to your photoelectric effect, state what is meant by work function energy. So work function energy is simply the minimum energy required to remove an electron from the surface of a metal. Okay, now this one here is a question from 2019, but in the years after that, when it asks you to define what is work function energy, there was one particular addition to the definition that they specifically wanted. Instead of saying minimum energy required to remove electron from the surface of a metal, the subsequent marking schemes in the later years require you to say minimum energy of photon required to remove electron from the metal surface. This one will be both the subsequent years when they ask you to define what is work function energy. They, for some reason, needed you to write minimum energy of photon, not just minimum energy. They want you to be a bit more specific here. Okay. Then if you're okay with that, then let's have a look at part B. Now in part B, they told you that the work function energy of a clean metal surface is 5.5 times 10 power minus 19 joules. Electromagnetic radiation of wavelength 280 nanometer is incident on the metal surface. And this metal is inside a vacuum. All right. There's nothing around your metal surface here. From there, calculate out your photon energy. Okay. For the electromagnetic radiation of wavelength 280 nanometer that is now incident on your metal surface. Okay. Your photon energy here is actually from your electromagnetic radiation, because here we already know that when it comes to electromagnetic radiation, it consists of photons. Okay, they want you to calculate the energy of the photon inside your EM radiation here. So since they gave you information about your wavelength, your photon energy by right should be hc over lambda. Use the one with a lambda term inside. So as usual, Planck constant is 6.63 times 10 power minus 34. Speed of light is 3 times 10 power 8. divide it by your wavelength. Remember to change it from nanometer to meter, so you multiply with 10 power minus 9. So eventually you get your answer as 7.1 times 10 power minus 19 joules, giving you this answer here. All right, so that part is pretty straightforward. Okay, then next part here is number 2. Find out the maximum speed Vmax of the electrons emitted from the surface. Okay, so be careful about the term that they use. They're not asking you to find the maximum KE. They're asking you to find the maximum speed, which is actually derived from your maximum KE in the first place. So you use your photoelectric equation, the general form of it. Photon energy is equals to work function plus your KE max. This one is actually supposed to be your KE max, but you expand it to become half m v max squared. That's why you have it in this form right now. So your photon energy, you already found it from the question above, is 7.1 times 10 power minus 19. Your work function energy is given at the beginning of your question. They told you it's 5.5 times 10 power minus 19. Okay, so sub that value in plus half times the mass of your electron, then multiply with Vmax squared. Okay, so this one here is KE max of your emitted electrons. So when it comes to the mass, you must use the mass of your electron. Okay, which again you can get from the second page of your exam paper, from your data sheet. Okay, so eventually your Vmax will just be 5.93 times 10 power 5 meter per second. Just like that. It's a pretty simple working for 3 marks. Then next part of your question, explain why most of your emitted electrons will have a speed lower than Vmax. It's a bit similar to the previous questions that you have done before, where they ask you to explain why your KE of some electrons is less than the maximum. This one is something similar. They're asking you to explain why the speed of some electrons emitted is less than the maximum. So you will use back the similar answer where you say that energy is required to bring electrons to the surface in the first place. So less energy, less photon energy remaining to be converted to KE and hence lesser speed. Okay, that is another way to think of it if you want to explain further. So this part should be okay. And then you look at the next part, this one has some table related to your photoelectric emission and intensity. So see, in part C here, they mentioned that the electromagnetic radiation incident on a metal surface may change in intensity or in frequency. Okay, so complete the figure below by inserting either increases, decreases, or no change to describe the effect of the changes shown on the maximum speed of your photoelectrons and on the rate of emission of your photoelectrons or your electrons itself. Okay, so let's just look at the first line of your table where they told you that you reduce your intensity but at constant frequency. How would it affect the maximum speed of your electrons? And how would it also affect the rate of emission of electrons? Okay, so let's just consider the case where you have reduced intensity at constant frequency. Now, photon energy is HF. Because your frequency is constant now, obviously your photon energy is constant. All right. Needless to say, your Planck constant is a constant also. This one is really understood. So your E actually really just depends on your F. If your frequency is constant, your photon energy must be constant. And you know that your electron gains energy from your photon, which is then converted to KE. So because your energy of photon is unchanged, your KE max that you get is therefore unchanged. So therefore, max speed is unchanged too. So this one, no change. But how about the rate of emission of electrons? So it's something similar to what we've done just now. When you're talking about intensity, is total photon energy divided by T then multiplied with A. That becomes N times E divided by T times A. Your photon energy now is constant because you already deduce it from the part above here. And then your area here is also assumed to be constant. So right now, you could say that intensity is directly proportional to the photons per unit time. They did mention to you that you have reduced intensity now. Intensity is reduced. So I decreases, your photons per unit time is decreasing. So you have less photons per unit time incident on the metal. You therefore must have less electrons emitted. So for your rate of emission electrons, this one was therefore be decreasing. Okay. Then how about the case where you suddenly have it the other way around, where your frequency is increased, but your intensity is constant. Okay. So for the case where you now have increased frequency, but at constant intensity, the line of working is the same. Since E is equal to HF, E depends on your frequency. Since Planck constant is constant here, your frequency increase, your E increase. Your electrons are receiving a higher photon energy. It must therefore result in higher KE of your electrons and therefore higher max speed. So therefore, your answer for the second row is that your maximum speed of your electrons must be increasing. But if you're talking about your intensity now, you again must refer to the equation for your intensity, where it's N times E divided by T times A. Now, different from the previous case now, they specifically told you that your intensity is constant, and you also assume that your area is constant now. You can then say that your photon energy is actually inversely proportional to the number of photons per unit time. Okay. From the top part here, you already know that your photon energy has increased. So if your photon energy has increased here, your number of photons per unit time must therefore decrease. Okay, so here you would have less photons per unit time incident on your metal, therefore less electrons emitted. Your rate of emission of electrons is therefore decreasing here. Okay, so that is how you would do this. It's worth 4 marks. All right. Okay, this one, next question you can have a look at is page 1. So you look at page 1. Let me just write it out for you first. You just have a look at page 1. This is June 15, P41, okay? Now for your particular case here, they mentioned that you have photon of wavelength 6.5 times 10 power minus 12 meter incident on an isolated stationary electron as illustrated in the figure below. Your photon is deflected elastically by electron of mass ME, and the wavelength of your deflected photon is 6.84 times 10 power minus 12 meter. Calculate for the incident photon is momentum. Okay, so in your case here, what they mention is that you have a photon coming over this way, all right, and then after that it hits a stationary electron. Okay, it hits a stationary electron. So this part here can be considered as something like before your collision. Then after that, your electron would definitely move away somewhere, but it's not indicated in your diagram here. What they did indicate is that your photon actually move away after the deflection, after the collision. So this part here, you can actually kind of consider it as after your collision. So right now, for your case, for the incident photon, they ask you to calculate out is momentum. Okay, now for the momentum part of the photon, this one is actually covered under the broad wavelength. I actually haven't covered it to you, but I can just tell you right now first that if you're trying to find out the momentum of a photon, there's a particular equation that you will use, which is this one. Lambda is equals to h over p. That equation is actually called your de Broglie wavelength equation. If you're interested to find out the wavelength of, sorry, if you're interested to find out the momentum of a particular photon, you tend to use this de Broglie wavelength equation, which I will explain in the later lesson. Okay, so right now you just want to find out the momentum of your photon. You use lambda equals to h over p. P here is actually your momentum that you are trying to find. Okay, so let me just write it here. This one, P here, is actually the momentum that you're trying to find. So is the ratio of your Planck constant to the wavelength of your photon. Okay, so Planck constant is 6.63 times 10 power minus 34 divided by your wavelength of 6.5 times 10 power minus 12. You'll be using this wavelength because they want you to calculate for the incident photon. So for the incident photon, it's actually referring to the photon before collision. So you must use that wavelength. All right. So your momentum here eventually will work out to become 1.02 times 10 power minus 22 Newton second. Okay, this is your momentum. Okay, then next part, they want you to calculate out the energy of your incident photon. Your energy here is still the energy of your incident photon, the photon before your collision. So E is equals to hc over lambda. Sum in your value of Planck constant, sum in the value for your speed of light, divide it by your wavelength. Eventually, you will get the answer is 3.06 times 10 power minus 14 joules, just like that. Okay, so again, this is pretty straightforward. This two is 2 marks already, just for simple substitution of your equation. Okay, then if you move on to part B, now for part B, they mentioned that the angle theta through which your photon is deflected is given by this expression, delta lambda is h over mec multiplied with 1 minus cos theta, where your delta lambda is the change in wavelength of your photon, h is your Planck constant, and c is the speed of light in free space. From there, calculate out your angle theta. This one is pretty straightforward. You just need to use the equation that they've given to you, sub in all the relevant values. Okay, so in your case, if you look at the first term in the equation, your delta lambda is the change in wavelength of your photon. You really do know the wavelengths before and after the collision. It was 6.5 times 10 power minus 12 before this, and then after that it became 6.84 times 10 power minus 12. There's actually an increase in wavelength here. Okay, so try to sub in the values. You can factorize out the power of 10. It's 6.84 minus 6.5 times 10 power minus 12. This is the change in wavelength. And then the rest of the values is something you can get from your data sheet. H is 6.63 times 10 power minus 34. Mass of electron is 9.11 times 10 power minus 31. Speed of light is 3 times 10 power 8. Then subsequently multiply all these with 1 minus cos theta. Cos theta will be this value, eventually giving you your theta as 30.7 degrees. Okay, so this is really just a matter of you substituting the values into a given equation to get the answer. Okay, now part 2 is your state and explain question. Use energy considerations to suggest why your delta lambda is always positive. Okay, now when your delta lambda or change in wavelength is positive, this implies that there is an increase in wavelength. Okay, when they told you your delta lambda here is positive, your change in wavelength is positive, that means it's an increase in your wavelength. You're trying to explain right now why is there an increase in wavelength in the first place? Okay, now before you can go to that, you need to relate wavelength with energy first. This one has something to do with your photon energy equation, where you know that E is equals to hc over lambda, where if h and c are constant, h and c are constant, E is inversely proportional to wavelength. Okay, so this is the two relation that you just need to know first. So let's consider what's happening before this. You had a photon that went and collided with a stationary electron. Okay, it went and collided with a stationary electron. This electron was stationary. Let's consider this as before your collision. Then after collision, what happened was that your photon suddenly started moving in this direction. And you can also safely assume that the electron, after collision, probably moves somewhere downwards. Okay, this part here, you can consider as after collision. Okay, so let's just consider this now. When you talk about the case before the collision, your photon here has a certain energy. This one has energy, but your electron here being stationary, it has no energy. Okay, after collision, both of them by right should move away. So this one still has energy. And then the electron here, before this, it has no energy. This one has suddenly gained energy. Okay. Specifically, the energy that you're talking about here is your CAIE. All right. This one is gain energy. So by looking at your situation right now, if you're talking about the electron before and after the collision, before this, it has no energy. Then suddenly after collision, it gained energy. It must have gotten the energy from somewhere. So in your case, the energy gained by your electron must have come from your photon in the first place, according to conservation of energy. Okay, your energy cannot just come from nothing. It must have come from somewhere right now. It actually came from your photon energy. So right now, what you can then say is something like this. If you try to like write out some sort of conservation of energy equation, your energy of photon before collision is equals to your energy of your photon after collision plus the energy of your electron, such that the energy of your electron is actually the difference in energy of your photon. That is one thing you can actually kind of see from here. Let's just assume that this one is energy of photon before collision, and then this one is energy of photon after collision. Your energy of your electron is actually the difference in energy of your photon. Okay, but the one thing that you are really interested here is from this equation here. Okay, if you're talking about your conservation of energy equation here, your energy of your photon initially actually got split out to your energy of your photon after collision, as well as your energy of your electron. So what you're interested to know here is what's the relation between the energy of photon before collision and energy of photon after collision. After your collision, because your photon energy before this is now being split up to your photon and electron after collision, what you could say is that photon energy after collision is less than before collision, since some energy has been shared with your electron. Okay, so this one, let me just erase it. This one I could probably say photon energy after collision is less than before collision, since photon energy has been shared to your electron. Okay, so photon energy after collision now being less than before collision, this you can now then relate to your previous point. If your energy of your photon is now less after collision, your wavelength must therefore increase, no? Therefore, change in wavelength is positive. Okay, your change in wavelength is positive. That's how you kind of relate your points here. Okay, so how you want to write your answer, you can write something like this. Your deflected electron in the first place has energy. This energy is actually derived or received from your incident photon. Your deflected photon therefore has less energy and thus a longer wavelength. Your wavelength increases, in other words. Therefore, your delta lambda is always going to be positive. Okay, so that is for this particular question. Okay, then you look at a next question. This one is under page 3. Then after that, we can move on to line spectra. Okay, so next question that we will look at is page 3. It's actually similar to the one in page 1. I can reuse back some of the points that I have written here. So this is June 15 P42. Okay. So for this particular question, explain what is meant by a photon. A photon is just simply a packet of energy of electromagnetic radiation. Okay, that's all there is to it. But if, say, for example, they ask you to define what is a photon, and you notice that the marks that is given to you is not 2 marks, but rather 3 marks, you will need to add another additional statement where you define out the equation for energy of a photon. Meaning to say, if you're talking about your question being worth 2 marks, you will just write the first line only. Okay, it's a packet of energy of electromagnetic radiation. But if it's a 3-mark question, you need to write another additional statement which is covering the energy of your photon in equation form, where you say that the energy of your photon is equals to the product of Planck constant multiplied with the frequency of your EM radiation. This one is if it's a 3-mark question. I believe the 3-mark question was actually for an older past year. At that time, when it was 3 marks, you needed to write the E equals to HF. That's where the extra mark came from. Okay. So this is for this part. Okay, then you move on to B. So if you just move on to B right now. For part B, they tell you that you now have an X-ray photon of energy 3.06 times 10 power minus 14 joules that is incident on an isolated stationary electron as illustrated in figure 6.1. They tell you that the photon is deflected elastically by the electron through an angle of theta. The deflected photon has a wavelength of 6.8 times 10 power minus 12 meter. And then on figure 6.1, draw an arrow to indicate a possible initial direction of motion of the electron after the photon has been deflected. Okay, this one I don't think I need all this diagram anymore. I can just use this diagram as it is. So for your case, draw an arrow to indicate a possible initial direction of motion of the electron after photon has been deflected. Your photon is this one. Your electron is this thing here. This is the case before collision. This part here is the case after collision. So after collision, you know that your photon deflected this way. But how about the electron? Your electron by right should be deflected downwards. But how do I know it must deflect downwards in the first place? Why can't I say it goes forward like this, or why can't I say it goes upwards too? It's because it's related to your conservation of momentum. If you just look at the case before collision, you just look at the vertical momentum. Before collision, the vertical momentum is actually zero. You can see that the photon was just moving horizontally, and then your electron was actually stationary. They've already told you that your electron was stationary right over here. Okay, so you do not have any vertical momentum before collision. So according to conservation of momentum, then your vertical momentum after collision must also be zero. This one I think I wrote the symbol wrongly. This one is vertical momentum before collision. This one is vertical momentum after collision. So after collision, your vertical momentum must also be zero, because this is actually related to your conservation of momentum that you have from AS. So your vertical momentum before collision is zero. Your vertical momentum after collision must also be zero. So like right now, if you just look at your photon, you have an upwards vertical momentum. It follows that your electron must have downward vertical momentum so that total momentum vertically remains at zero. That's the reason why I know it must deflect downwards, so that my total vertical momentum remains at zero. Okay? That's why you cannot say that it just moves forward like this or it goes outwards like this. You still have to follow conservation of momentum. Okay? Okay, then after that, you move on to part 2. Calculate out the energy of your deflected photons. So let me erase some of those stuff here. So what you want to know now is the energy of your deflected photon. Okay, so this one is a bit different than the one that you just did earlier. The one in page 1, it also asks you to calculate out the energy of your photon over here, but that one is for the incident photon, the photon before collision. So in your current question, it's also energy of photon, but they want the energy of your deflected photon, the one after collision. So it pays to read your question carefully. Which photon are you referring to? So right now, they want the energy of your deflected photon. You again just use E equals to hc over lambda. Just sum in your relevant values for your Planck constant, for your speed of light, divide by your wavelength. The wavelength that you use is this wavelength at the top here. Eventually, you get your answer as 2.93 times 10 power minus 14 joules. Okay, so this one is pretty straightforward. Okay, then after that, you come to the second part where we want you to find out the speed of your electron after the photon has been deflected. Okay, so for this part here, based on the diagram that I just drew for you earlier, maybe I just draw it very quickly here for you. Your photon was moving this way towards an electron that was stationary. This one was before collision. Then immediately after your collision, what you got at the end was that your photon now moves upwards, whereas your electron now moves downwards. So what you are interested in is the electron, the energy of your electron right now. Your electron here was stationary. So this one here was stationary. So this one has no energy. But after that, it started moving after the collision with a certain velocity v. This is the v that you are trying to find out. So for your electron here now, you actually have CAIE. Okay. So right now, if you're talking about your electron energy now, as I mentioned to you just now in detail, your electron energy actually came from your photon energy in the first place. Your photon actually gave some of its energy to your electron. And then after it gave some of its energy to your electron, the photon energy decreased. So this one, let me just write something here. From here to here, your photon energy decreased because it was shared with electron. Okay. Then after that, from here to here, your electron gain some energy from your photon. It gains some energy only from your photon, not all of your energy. Okay. That's why it's proper to say that it's gaining some energy only. So your energy of electron here is actually really the change in energy of your photon. Okay. So you want to find out the change in energy of your photon here. That one will be your electron energy. That one is actually listed here already. The energy of electron is your initial photon energy minus your final photon energy. You already know the values of your energy already. Your energy of your deflected photon is already found here. The energy of your initial electron is already in the diagram there. So you take the difference between those two, you will be able to find out your energy of your electrons now. Okay, so it will be 3.06 minus 2.93 times 10 power minus 14 joules, giving you 1.3 times 10 power minus 15 joules. And this energy of electron that you have is actually in the form of KE, in the form of kinetic energy. So you can therefore say that your energy of electron is half mv squared. Your energy of electron gain is 1.3 times 10 power minus 15. Your kinetic energy of electron is half times its mass multiplied with your speed. Eventually, you get 5.34 times 10 power 7 meter per second squared. So because you're talking about electron now, you are going to use the mass of an electron. All right, so this one is for this particular question. Then there's another part to it too. So let me just move on to the next part. Now for part C, explain why the magnitude of the final momentum of the electron is not going to be equal to the change in momentum of the photon. Okay, why is it that the final momentum of your electron isn't the same as the change in magnitude of momentum of the photon? The reason for that is because momentum is a vector. So let me just give you a very simple example. If let's just say, for example, I tell you that I have something that moves with a momentum of 3 Newton second. And then after that, it suddenly moves with a momentum of 4 Newton second upwards, perpendicular to my first momentum. If I then ask you, what is the resultant momentum here? I cannot just simply say that the resultant is 3 plus 4 giving me 7, right? Because this is a vector. What you learned in the first chapter of your AS physics last time was that when you're dealing with vectors, you need to consider their direction. You cannot just simply add their magnitudes. You cannot just simply minus the magnitudes, especially if their directions are different. So like in the example here, you have 3 Newton seconds towards the right and 4 Newton seconds upwards. I cannot say that the resultant here is 7 Newton seconds. I cannot just simply say this. This is definitely wrong. You cannot simply add the magnitudes. So what you learned last time was that if I wanted to find the resultant, then I would have to draw the vectors from head to tail. Like in your case, the resultant is actually going to be this one. And because I noticed that it's the right angle triangle, my resultant here is actually going to be square root of 3 square plus 4 square, giving me 5 Newton second. This one is going to be my resultant momentum here. And you can see that this one is clearly not you adding the magnitudes together. Okay, so it's a similar thing right now when they're talking about this question. Why is it that the final momentum of your electron is not equals to the change in magnitude of the momentum of your photon? Is simply due to the fact that momentum is a vector quantity in the first place. You have direction changes here to consider. You cannot just consider the magnitude. You actually would eventually need to consider the momentum in two directions, x and y. But this first two statements alone is already enough. You must first identify the momentum is a vector. You have to consider direction also, not just the magnitude. Okay, so that one is for this particular question.